Continuing a bit where you left off last time, we're talking now about formalizing relations and functions. So we're going to do two things. We're going to determine whether a relation is a function, and we're also going to find domain and range to use function notation. So that first part, when we're talking about a relation is a pairing of numbers in one set that we call the domain with numbers in another set that we call the range. So relations often represented by the set of ordered pairs x and y. Again, these are the values that you see on a graph, your x and y values. In this case, the domain is what we refer to as the set of your x values, and the range is going to be your set of y values. And that's going to be pretty consistent. So domain, you want to think x's, range, you always want to think y's. Function is a special type of relation in which each value of the domain is paired with exactly one value in the range. So again, we can have different types of relations, but a function has to follow that rule. I can't reuse a domain value with different range values. So looking at this example, identify the domain and range of each relation, represent the relation with a mapping diagram, and lastly, we need to tell is that relation a function. So in that first example, we see 4.2 and 1.5 are your x and y values. So if I take the x value from that, that will be a value of the domain. Next is 5 and 2.2, so 5 is another domain value for x. 7 and 4.8, so 7 is another x value for domain. And 4.20 means that 4.2 is already used. We don't need to use that again as the domain because that first ordered pair covered that already. So again, we can do the same thing with the y's. If I took all the x's from my domain, 4.2, 5, and 7, my y values are just going to be 0, so I just go in order from least to greatest. 0, 1.5, 2.2, and 4.8. That means that's my range, all my y values. As far as the mapping diagram goes, that's a little bit easier than it sounds. Mapping diagram just means if I put all of my domain values in one group, so my domain I have 4.2, 5, and 7. All my range values in the other group, 0, 1.5, 2.2, and 4.8. What it means to map from one value to the other is that if I start with a domain of 4.2, I see from my relation that 4.2 used a range value of 1.5, so I draw an arrow from 4.2 to 1.5. And for my next number, I have 5 and 2.2, so from 5 I can go to 2.2 in the range. If I start from 7 in the domain, that means I'm mapping that to 4.8 in the range. And 4.2 we see again maps also to 0. So that issue there, if I see that one domain value, 4.2, is being mapped to two different range values, I can tell that this is not going to be a function. Because again, for a function to work, I need to have the domain values to all have one range value. And we see that 4.2 has two pairs. So I should only see one arrow at a time going from my domain to my range. Same example in the next situation. If I have -1, 1, that means my domain is -1. That's your x values. And again, the other ones I can find the same way. So -2, 4, and 7 are your other x values. Those are all my domains. Range, again, in order from least to greatest, I have -7 in my range. Another y value is -4, 1, and 2 are all of your y values. But this time, if I put that into a mapping diagram, again, with your domains in one group and your range in the other, I see that when I map my points, so -1 maps to 1, -2 maps to 2, 4 paired with -4, and 7 paired with -7. Here, since it seems that each domain value is only going to one range value, this will be a function. Again, since every value in the domain has just one member in that range. I don't have a split like we did in that last time where 4.2 is used twice for two different ranges. So also another way that we can test other than with that domain test is something we call the vertical line test. So again, if I analyze a graph of a relation, I can tell if it's a function if I use something we call that vertical line test. And what that test does is I see if any vertical line passes through more than one point on the graph. Then for some domain value, that means there'd be more than one range value. So kind of like that situation we had in that first example. That would mean that the relation is not a function. So again, what we're looking for is we're going to draw vertical lines through our graph, and if that vertical line hits more than once on your function, that means it's not going to be a function. So if it hits more than once on the relation. And if I'm using that to test if the relation is a function, when it says to use the vertical line test, that just means I need to put that into a graph. So 4, 2, graph right here, 1, 2, 0, 1, -2, 2, and 3, 3. Just make sure I have all my points in the right place. And then again, vertical line test means if I draw vertical lines through all the points on my graph, I can see that at no point does a vertical line hit more than 1 point, so that passes my vertical line test. That will be a function. And I also drew a vertical line here to show that if I draw a vertical line that doesn't go through any points, that still means it could be a function. So again, it's all right if it doesn't pass through any. As long as it doesn't pass through more than one, we're all right. In the next example, if I start graphing those points, 0, 2, 1, negative 1, negative 1, 4, 0, negative 3, and 2, 1, it looks like when I start drawing vertical lines here, I draw those through my points, but when I drew this vertical line through my y-axis, so when your x's are 0, it looks like that vertical line passes through a point here, and it passes through the point below. So since that vertical line passes through 0, 2, and 0, negative 3, 2 points from my relation, I can see that this will not be a function. The same line goes through 2 spots. So we've also seen functions represented as equations when we're using x and y, so we're working graphing stuff like this before. But below we can use the same equation, but we can write that instead in something we call function notation. And the way we're going to read that, so first of all we notice that we have this symbol replacing y, so the only thing that changes is I take y and I replace it with something we call f of x. So if I see that symbol, it looks like f times x, but again this is not a multiplication. This is just the name of this function. So f of x is basically what we call that function name. So letter f is the name of a function, not a variable. So a lot of people make that mistake when they multiply them, but you want to make sure that we're just using this as a name. So function notation is used to emphasize that the function value, so f of x, depends on the independent variable. So whatever I plug in for x, that's going to give me a result for the value f of x. Other letters besides f can also be used, such as g and h. So again, that just means that we can name this function different names and it'll still work. In our couple examples, we can see that first function, w of x, again we read that of x, w of x equals 250x, represents the number of words, w of x, we can read in x minutes. So how many words can you read in 6 minutes just becomes plugging in that value. Again, if x just represents minutes, that means if I replace x with 6, then I'm looking for this value of the function when x is 6. So all I do is do 250 times 6, and that tells me that I can read 1,500 words in 6 minutes. So for that next question, if I know the domain of that function, 4x minus 12, is 1357. Remember, domain is going to mean your x values. So if I use those as my x values, if I replace x with 1, I get 4 times 1 minus 12, so that should be negative 8. If I replace x with 3, 4 times 3 is 12, so 12 minus 12 is 0. If I replace it with 5, 5 times 4 is 20, minus 12, I get 8. And replacing that with the last domain value, 7, I get 4 times 7 is 28, minus 12, I get 16. So as long as I'm plugging in each one of those domain values, I'm substituting those into my function, I can see that I have those 4 range values. So negative 8, 0, 8, and 16. We can list those as a set, just like we did with the domain. So last question here comes in 2 parts. We have 7 quarts of paint to paint the trim of my house. A quart of paint covers 100 square feet, and the function a of q equals 100q represents the area, a of q in square feet, that we use q quarts of paint to cover. So what domain and range are reasonable for the function? Again, when we think real-life examples, they have to be reasonable. And we also want to graph that function. So graphing basically the same rule like we've done before. So as far as thinking of the reasonable aspects, again, if your domain, that's your input value. So q is going to be my domain variable. And if I want to think of what values are reasonable for q, we're kind of answering 3b already in this question. So you can kind of answer 3b before you answer 3a. If I'm using a domain, again, it looks like my domain, q has to be between 0 and 7 inclusive. And the reason for that is if q is representing the quarts of paint that I'm using, I can't use negative paint, so 0's got to be the lowest amount that I can use. And it says in the question that I have 7 quarts of paint total to paint the trim of my house, so I can't go over 7. I can go all the way up to 7, but I can't go over that amount. So if I'm thinking of the domain that I can use that's reasonable, again, can't go negative, can't go over my amount of paint, so q is in between those 2 inclusive. And then to figure out your range, all you have to do is take the lowest value, plug that into your function. So if I plug in 0 quarts of paint, it looks like 100 times 0 is 0 for the area, which makes sense. And if I plug in 7 quarts of paint, 100 times 7 would be 700 for that area. So it looks like for that range values, that can be as low as 0 and as high as 700 if I use all of that paint. If I'm just putting this into an equation, into a graph, again, we just want to make sure my independent variables along the horizontal axis, so that's your domains, your Q, and my area that goes along the dependent axis, so my vertical axis. And all I have to do, again, I can take 0 and 700, plug those in, and I can also figure out some values along the way. If I plug in 1, I get 100, 2 is 200, 3, 4, 5, 6, all follow that same pattern, so 300, 400, 500, 600. And we can also graph this as continuous, again, because you can use different amounts of paint. We don't have to use like 1 quart or 2 quarts or 3 quarts. I can use 1.4, like 2.7, or any amount between those, so I can connect those with a continuous line. So make sure that you have these notes filled in. Again, that was the last part, is just making sure that we could fill in that graph, and we'll work on some of that practice next week.